Okay. So let's start with oh, there's nobody taking care of questions. Ah, no. Okay. All right. So let's start with the last lecture of this mini course, which is about applications to QCD. That was the original motivation of AdS-CFT, although in recent years it has become less important somewhat. So, like in the case of condensed matter, we still have two kinds of models, top-down and bottom-up. Top-down meaning dualities that were derived in string theory from some decoupled system of brains, so system of brains in some decoupling limit. And bottom-up, which are like for AdS-CFT, phenomenological models. We invent some gravity model that, assuming the holographic map, should correspond to a field theory with some desired properties. It's just that in these applications to QCD, we have several models that are of the first kind, top-down. Although we do have also bottom-up models, so we'll describe both. All right, so let's start with top-down. Well, I told you that for QCD, to describe QCD, which has a mass gap, we need to cut out some small cylinder from the middle of the AdS cylinder via some procedure. And one such procedure was by introducing finite temperature, by considering the AdS black hole, and specifically the Witten model for the AdS black hole with some scaling that corresponded to an infinite mass. So we've written the the model metric, which is there on page 202. And this finite temperature, the Witten model, this satisfies the minimal ingredients for QCD duals. It has this cutoff, so the cutoff R minimum is given by the horizon, so R horizon. Then the other model that we've also described is simply the cutoff AdS5. So R minimum, R horizon here. Cutoff AdS5. This went under the name of hard wall model because there was a hard cutoff introduced by hand at R minimum that's related to lambda QCD. We can make an improvement on this cutoff AdS5 model by making the cutoff dynamical. That is to say, making it a brane, some D brane at R minimum. Then the So the fluctuation, so let's say at R minimum, so if I plot, let's say, the warp factor, and here is R, at R minimum, I put this brane that fluctuates, then the fluctuation modes of the brane, the transverse axes, are scalars from the point of view of the theory on the brane. And these scalars, on the other hand, should correspond, according to the general map that was described for gravity duals, to pion-like operators. So position correspond to the D-brane position to pion-like operators. And in fact, we can also obtain, if we consider this position, we can also obtain a relatively good model for the pion that gives a precise version of the saturation of the Froissart unitarity bound. The Froissart unitarity bound is sigma less than equal than pi over m pi squared log squared s over s0. So total cross section for scattering is bounded by a log squared behavior with the coefficient being less or equal to pi over m pi squared. So one can obtain a saturation of that. It was in the slides, but I haven't discussed it. So these are the two simplest models. And then people started looking for more complicated models that have properties closer to QCD, in particular running of the coupling. That's an important property. So the mass gap is an important property, but also running of the coupling is an important property of QCD. And so one of the first models that appeared was the Polchinski-Strassler model. So, of course, QCD is very hard to obtain. It's both non-conformal and non-supersymmetric, and it has NC equals 3. So when we say QCD, we really mean QCD-like theory. And so the hope was to describe n equal 1 supersymmetric QCD at large at NC. So if we would have this, then already that would be an enormous progress. But as I'll explain to you, all of the models claimed to do that, but in the end failed because of technical reasons. So I'll explain that a little bit. So the Polchinski-Strassler solution also wanted to obtain that, but even a little bit less, so not QCD in the sense of super-Yang-Mills plus quarks, but just super-Yang-Mills. So it wanted to describe this, but in the end describes something that we'll call n equal 1 super-Yang-Mills star, which is a deformation of super-Yang-Mills. So this is some mass deformation of n equal 4 super-Yang-Mills. But actually the problem is that it contains an infinite amount, an infinite tower of massive fields that are not supposed to be there. So the configuration that one considers is D3 branes with some flux. And if you put a flux on some compact space, the compact space sort of, if you, the compact space, sorry, if you put some flux in a space that naturally would have been compact, even if it's zero, this will sort of grow or puff up or polarize. And that is what happens in this case. The solution, the specific solution is written in this page 203. But I would point out that is described by two factors that are sort of harmonic-like in terms of two coordinates, rho plus minus, that are some combination of radial coordinates, also written there. So here I have 1 over r plus squared and r minus squared, and in z omega I have r minus squared over r minus squared plus rho minus squared plus rho c squared, everything squared. So the one important property is that at large rho, which is the common value of rho minus and rho plus. So you see from the definition, if y and w are very large, so rho plus and rho minus are very large, then I can ignore rho 0 and the two become the same thing. And then the metric becomes AdS-5 cross S5 with a small, with corrections that appear when you go away from it. So that is of the type that we've described. So we said that any theory, if we go into ultraviolet, looks approximately conformal. So rho going to infinity. So rho going to infinity means ultraviolet. So in the ultraviolet, we should certainly have AdS-5 cross S5. And on the other hand, because of these formulas and the fact that rho plus minus, so y squared plus w plus minus r0 squared to 1/2, this becomes equal to rho 0 in the infrared. So rho going to r0 in the infrared, which means that the warp factors are finite. And this is the origin of the fact that we have mass gap. So like in these kind of theories, for instance, just the cutoff AdS-5, the warp factor stayed finite just because we cut off the metric at this R minimum. And this natural scale was related to the scale for the mass gap. Well, actually, the relation was this, but implicitly, R minimum was related to the warp factor. So the warp factor was capital R squared over R minimum squared. So the same thing happens in here. We have finite warp factors, which means we have a theory with a mass gap. All right, so This is nice, but as I said, this is not really not even n equal 1 spare Mills. This star means that, in fact, we have an infinite tower of Kaluza-Klein fields coming from expansion on a sphere. Then we have the Klebanov-Strassler solution. So Klebanov-Strassler. Which is n equal 1 supersymmetric, but not SUN, but rather SUN plus M cross SUN with chiral bifundamentals. So bifundamentals in fundamental of one and the other gauge group. So in the fundamental of the first group and anti-fundamental of the other. And then other bifundamentals in the complex conjugate one. And the brane configuration in this case is, so the fact that we have this product gauge group is because we have M so-called fractional D3 branes. So D3 branes wrapping a vanishingly small cycle or volume. So volume that goes to 0, specifically goes to 0 at a point called the conifold point. These are many technical details that don't matter too much. I mean, matters if you want to understand how you construct this, but for what I want to say, they don't matter too much. But what matters is the fact that I have this product gauge group, and it results, excuse me, it results in a very interesting physical property called the duality cascade. So n equal 1 theories with some SU gauge group and some fundamental chiral superfields obey so-called Seiberg duality, which means when you go to some appropriate infrared region, so low energy region, the effective theory jumps from being the original one to one with a gauge group, with a different gauge group, when the gauge group would have, so SU NF minus NC and the same NF flavors. But then, since in this case we have a product gauge group and we have bifundamentals, so these would be NFs. Then one effectively obtains this cascade of dualities. So one just changes the gauge group, both gauge groups with a factor of m. So one goes into SUN cross SUN minus m. So SUN plus m cross SUN goes to SU n cross SU n minus m, and then applying the duality cascade by going further in the, applying again a duality by going even further in the infrared, one obtains SU n minus m cross SU n minus 2m, and so on, until at some point the duality stops, in the sense that if I would apply it again, I would get SU of some negative number. Okay. So that means that at this duality cascade means that at different energy scales, I have different effective gauge groups. And this time the solution is even more complicated. It's written there on page 204. But the one observation that I would make, so when I was describing the general property of gravity duals that are QCD-like, I was saying that in the UV, this could look conformal, but maybe there's some correction to it. And this is such a case. So in this case, at large tau, which is tau in this case is radial type coordinate, as one can find there. Well, I will not write this down, but you can see ds6 contains d tau squared, so that's a radial-like coordinate, and all the other functions depend on tau. So then ds squared becomes log-corrected AdS-5 cross S5, meaning that the harmonic function is has this log of R minus R over Rs, and otherwise it's the standard one. So GSM squared over R4. So so remember, normally I would have here R4, which was GS 4 pi GSN squared alpha prime. But now I have this m in here instead of n, so GSM squared divided by R4. And now I also have this log correction for the harmonic function. Oh, sorry, yeah. It's not cross S5, but it's actually cross the space T11, which is S5 divided by some discrete group. I cannot remember now if it's, I think it's Z2 cross Z2. I cannot remember right now. So it's okay to having a space that's S5 divided by a discrete group. Wait. Yeah. So the log correction is now related to the renormalization. So this is related to the renormalization of the coupling constant. So the coupling constant, at least at one loop, a strong coupling constant at one loop is alpha s of, let's say, of Q, goes like log of Q, Q being some energy scale, right? And remember that R was R over alpha prime, which is U, was the energy scale, right? So Q perhaps. So this log R is really log Q, and it also appears like a coupling constant in front. So this log correction of AdS amounts to the fact that we have a theory with a running coupling constant similar to QCD. And moreover, now again in the infrared, we can obtain a finite solution with finite warp factor in front of dx squared. So now also in the infrared, so this was UV, and in the infrared I have ds squared, which is a0 squared dx31 squared plus dot dot dot. So this is now also finite, and the same argument as before, that the warp factor is finite, and like here, the warp factor was finite, and the finiteness of the warp factor was related to the presence of a mass gap. So this Klebanov-Strassler looks looks even better somehow, in the sense that has both the running coupling of QCD and the mass gap. Of course, on the other hand, it's not exactly the theory that we wanted. It's this kind of weird theory. It's SUN plus M cross SUN, and then two types of bifundamentals. But, you know, depends on your test. Here also has these bifundamentals, which contain quark-like objects. So it's a nice theory. Then, so historically, this was the evolution, the one that I wrote in here. First, finite temperature, then cutoff, then Polchinski-Strassler, then Klebanov-Strassler. And then I can remember this in 2000 or 2001? 2000, I think. Maldacena and Nunez, well, my co-organizer Carlos Nunez and Juan Maldacena, who will speak, they wrote what they hoped it would be, a dual of n equal 1 super-Yameos. I will put a question mark here because it's not quite that. So in fact, we will see that the question marks amount to having massive Kaluza-Klein modes. So the hope was that we would be able to find a region where the properties are kept, the properties of strong coupling, behavior are kept, and nevertheless we get rid of the Kaluza-Klein massive modes, but such a region does not exist. So the brane configuration in this case is, so this is in, if we consider in type 2b, NS5 branes. I told you a little bit, I think during the question session, what NS5 branes were. The magnetic version, so the magnetically charged under B mu nu, where the electrically charged is the fundamental string. Or another way of saying it, this is the S dual to D5 branes. So in fact, in this theory, you can describe it either, you can describe either the NS5 brane solution or the S dual D5 brane solution. So the solution, again, is complicated. It's written there on page 205. So I want to note that it's written in terms of a non-trivial function r squared of rho, where this is a radial coordinate. Yeah. And the solution is obtained, detail. This is obtained by uplifting. So one first writes a solution in 7 dimensions, and then uplifting it on an S3 to a solution in 10 dimensions. So uplift meaning the opposite of Kaluza-Klein reduction. And then on top of this, page 206, I've written the S-dual D5 brane solution. Well, the metric, rather. So, yeah, this is also written also in terms of an R squared of rho. Okay, so what I was saying is that there are massive modes over there that we cannot get rid of. So how is that? How does that go? Well, we can find the QCD string tension of the field theory, and this would be e to the dual phi at the boundary, 0, divided by 2 pi alpha prime. So this would be the G string. So the vev of e to the phi of the dilaton is the string coupling. So this is a sort of a coupling divided by 2 pi alpha prime. But then one finds that the mass of glue ball solution, so the glue ball solutions are, glue balls are things associated with operators like trace F mu squared. So these correspond to some scalar fields. So these operators couple to some scalar fields in the gravity side. And so we can obtain through the calculations of mass spectra. If you remember, I said that mass spectra are found basically as eigenmodes for the oscillation of fields in AdS. And then one finds that actually, unfortunately, the m squared for these glue balls is of the same order as the mass of Kaluza-Klein states, which are so 1 over the radius of an S2 squared. So I should have, yeah, okay. So you can see there the S2 appearing. So the point is, either in NS5 or D5 picture, I have, so the 5 brane wrapping an S2 gives a 3 brane for our true 3 plus 1 dimensional field theory. And the S2 is this one. And then this 1 over R2 squared is 1 over n alpha prime. So decoupling of these Kaluza-Klein states would mean to find that these Kaluza-Klein states would be very high. But what would that mean? So this much smaller than this would imply that e to the phi d0n is much smaller than 1, right? E to the phi d0n much smaller than 1. But this, we said, is some G-string dual. So GSN much smaller than 1, that's the opposite of the regime we're interested in. So this doesn't exist. So in other words, physically, what does it mean? It means that, so this is a string tension, a QCD string tension. So the QCD string tension is energy per unit length for the QCD flux tube, right? So the thing that defines the confining physics that we want, the QCD flux tube. And so we really want this to be, you know, if we want to study its physics, it must be much smaller than the physics of the other modes. We want to be able to throw them away, and we can't. In the UV of so for the UV of the quantum field theory at r goes to rho goes to infinity, in the case of this theory, this doesn't look exactly like what we said before, AdS-5 cross S5 times a log correction. So what does that, how is that possible? Well, so this is not AdS-5 cross S5, maybe time log corrections. But the solution to this puzzle is that phi, the dilaton, is non-trivial. And in the previous cases, the dilaton was trivial. So the dilaton being non-trivial means that when I write a string action, let me write it here, that included a g mu nu and also e minus 2 phi r mu nu. But then substituting for the, well, g mu nu times r mu nu is the Ricci scalar, substituting the background, we find in here that the relevant thing that appears is e to the 2a minus phi, where a is the warp, e to the 2a is the warp factor. So you see, if phi is trivial, the warp factor e to the 2a is the relevant thing. But if phi is non-trivial, the relevant factor is this. It's not anymore the warp factor. Okay? So the condition to have log-corrected AdS-5 cross S5 is now not, so e to the 2a is that appears in the metric, so for AdS. But I'm saying morally having AdS-5 is not about the metric, but about the metric times e to the minus 2 phi. And that has the correct behavior. It's a log plus corrections. Okay, so it's an interesting point. So naively, you look at this, it's a non-trivial thing, but then you realize that in fact, e to the 2a, the warp factor, times e to the minus 2 phi is log-corrected AdS-5. Okay, that's really the thing that matters. So this gravity dual is also of the type of log-corrected AdS-5 cross S5. And in the infrared, again, one finds that this effective warp factor e to the 2a minus 2 phi is constant. So the constant, also constant warp factor in the infrared. So all of these three gravity duals have the same properties. Log-corrected AdS-5 in the UV and constant warp factor leading to mass gap in the IR. Now, well, partly because I wrote this, but also partly because I think it's more interesting that it has an extra property. I describe the solution I wrote with Maldacena shortly after his solution with Carlos Núñez, which is an analog, but in one dimension less. So this would correspond to a 2+1 dimensional field theory. And the 2+1 dimensional field theory, let me see, let me remove this. So this is in 2+1 dimensional, 2+1 dimensional QFT, specifically n equal 1 super Yang-Mills plus, so with Chern-Simons terms, so super Yang-Mills plus Chern-Simons terms. But again, the same star issue applies exactly like in the case of Maldacena and Núñez, and for exactly the same reason as in here. We try to decouple the string tension from the Kaluza-Klein scale, and we cannot because of this condition. GSM needs to be large. So the brane configuration, in this case, brane configuration is also an S5 branes or D5 branes for the S dual. But now on S3, right? So before these 5 branes were wrapped on S2. Now they're wrapped on S3. And, well, the solution is written there. But there's one important point. These Chern-Simons terms have a level or quantized coefficient. So in 3 dimensions, the Chern-Simons term is trace A wedge dA plus A wedge A wedge A. But in the quantum theory, one can show that the coefficient needs to be a quantized integer divided by 2 pi. And this is known as the level of the Chern-Simons. So the Chern-Simons level, in this case, is K. And for the gravity dual, one considers K is equal to n over 2. And the important new ingredient, did I talk about it? Yeah, okay, so I'll talk about it on the next slide. So let's see the same story as before. So in the UV, the same thing. When rho goes to infinity, I look at the behavior of R squared rho, and I find again that this effective warp factor. So the warp factor type. The warp factor times E minus 2 phi. This one is log corrected AdS-5. And in the IR, when rho goes to 0, we find finite warp factor. This is finite. Okay, so this is the same thing as before. But the one new ingredient, which is what I thought was cool and interesting to put in here, because okay, if you're interested just in QCD, then you even don't want supersymmetry. But otherwise, if you're interested in supersymmetric theories, an important theory for theories that strong coupling is dynamical, that is non-perturbative, supersymmetry breaking. So this theory, even though it is in 3 dimensions, presents dynamical supersymmetry breaking. And the way this happens is extremely simple. I said that the gravity dual corresponds to a Chern-Simons level k equal to n over 2. And then let me add some little k, little n, I said, much smaller than n over 2, branes on a non-contractible S3. So then in the three-dimensional theory, that amounts to adding this little n to the Chern-Simons theory, to the level of the Chern-Simons theory. And one can figure out that if n is positive, in other words, I'm adding branes, not anti-branes, SUSY is preserved, whereas if n is negative, there's no SUSY. SUSY is broken. So this is a very simple model for supersymmetry breaking, for dynamical supersymmetry breaking, that was afterwards used in other places, for instance, in the KKLT model of cosmology, but in many other places people use this kind of idea. So dynamical supersymmetry breaking by adding a small, that is probe-like, a small number of branes or anti-branes. So for one having supersymmetry, for the other supersymmetry is broken. All right. So okay. So this was in the order of in the historical order. So we've reached 2001. Our paper is in 2001. And finally, let me consider what is considered the most phenomenologically useful top-down model, the Sakai-Sugimoto model. So this was 2005 or 6 or something like that. So until now, we've considered supersymmetric models. Well, no, the cutoff AdS-5 was not supersymmetric, and also the finite temperature was not supersymmetric, but those were too simple in some sense. So Klebanov-Strassler contains some sort of bifundamentals, but not exactly, those are not exactly good as describing quarks in QCD. But to describe quarks and to have supersymmetry breaking, one considers this Sakai-Sugimoto model. And okay, you know, as we said, we haven't even given a good, a totally acceptable gravity dual of super Mills, n equal 1 super Mills, let alone of just QCD. So in here, this comes with a caveat. So this is in a probe approximation. Remember I told you about how to introduce quarks via probe brains. And the point was that probe brains don't back react. So we take, so we have open strings because there are modes that either go from infinity to the brain or both open strings ends are on the brain. So we have open strings, but they are introduced, so these quarks or open strings are introduced in a way that is not dynamical. So they don't make part of the theory. They're just, we just consider them as some probe that does not change the theory. So what is the model? Well, one starts with a doubly Wick rotated Witten model. So the Witten model was for finite temperature, and we have double Wick rotated, so we had some time and some, let's say, x1, and we said that this becomes an Euclidean time, whereas this space coordinate becomes some time. Okay? So the metric there was u over r 3/2 f of u d tau squared plus dx4 squared, by which you mean minus dt tilde squared plus dx3 squared, plus r over u to the 3/2 du squared over f of u plus u squared d omega 4 squared. And you note that this is actually not AdS. So why is that? Well, it's not Wick rotated non-extremal version of AdS. Because when I say Witten model, I actually mean non-extremal, near extremal, near horizon, D4 brane. Since I want this coordinate to be identified with some extra compact coordinate, okay? So this, as you see, the world volume of the original theory in here was 5-dimensional. There's these 4 coordinates plus this 5th coordinate, right? So the wall volume in here was 5-dimensional, corresponding to a D4 brane. And we had, yeah, how to write this? We had like this, right? So the Witten solution, the near extremal near horizon D4 brane was with a minus sign in here, with a plus sign in here. And now we did the doubly Wick rotation, putting a minus sign in here, and this turning it into a plus. And then, as a further thing, we will consider this tau as a compact coordinate in which we'll do a Kaluza-Klein reduction. All right. And now comes the important point that allows us both to introduce quarks and to break supersymmetry. So both of these things come because we introduce a probe D8. Or more precisely, NF probe D8 branes, but NF much smaller than NC. So if you have a very small number of D8 branes, they're effectively probed, they don't curve the background. And we look for a D8 brane configuration where if this is the U direction, so this is infinity, and here I have U0, the horizon, I have a D8 brane that starts at the infinity, then goes in, and then goes back out. So you see, branes and strings, so all of these non-perturbative objects, they come with a direction, right? So if the direction is like this, I call this a D8. If the direction is upwards, I call this an anti-D8, right? So effectively, by the fact that I have this brane that curves back, I will have a D8 bar system, and that will break supersymmetry. Because, well, you can define what doesn't break supersymmetry by having the orientation being the same as the orientation of the things in the background, right? So I can choose, and my choice was to say this is the same one as the branes in the background, so this doesn't break supersymmetry, but this will break. And okay, so the other things you might ask, so why a D8 brane and not some other number? Well, the point is now, so there's only one transverse coordinate to a D8 brane, since it's 9-dimensional. And the transverse coordinate is this one, U. And so the brane wraps this omega-4, and is of course parallel to our 4 dimensions. Okay, so so that's one answer. The other is that a dp plus 4 solution is the only one that breaks only half the supersymmetry, so it's a supersymmetric configuration. And so in this case, D4, D8 is a supersymmetric configuration. But of course, once I introduce a D8 bar, then I'll break the supersymmetry. Yeah, and then you can find the shape of this, solving the solutions of. searching for the solutions of the equation motion of tau versus u. And then you ask for you want to calculate things in this Sakai-Sugimoto model. And so what can you consider? Well, so the modes on the D8 brane, for instance, the scalars corresponding to the perpendicular direction, or some gauge fields. So there are gauge fields on all branes, so there's some gauge fields in here, and there's these are vector, these correspond to vector mesons in the field theory. We described that. So this would be scalar mesons, and this would be vector mesons. Scalar mesons are something like the pions. So you can check that the same behavior is true for this Sakai-Sugimoto model as for the other ones. So if I look for the UV of the theory, that means at U going to infinity. I can, well, after a change of coordinates by writing rho equal square root of u and still going to infinity, we get the AdS, AdS 6, I guess, times S4, yeah, metric. And up to some conformal factor, and then that means that I can compactify the theory. So first of all on S4, as usual, but also on this extra coordinate tau that I say belongs to some circle. Then in the IR, so at u goes to u0, then we have a finite u. A finite warp factor. Okay, so this Sakai-Sugimoto model has the same behavior as the other ones. In the UV is AdS cross S. In the infrared, you get the finite warp factor. But how do we get now mass spectra? So this is slightly different than in the other cases. In the other cases, the mass spectra was obtained as simply the eigenmodes for various fields in the gravity dual. We just consider the wave equations for these fields, and we obtain a tower of state, a quantized tower of solutions. But now we have modes on the probe brane, and we can also look for the fluctuations in those probe branes. So, so yeah, I mean, so mass spectra. So I can look for glue balls. So those, so made out of just Young-Mills fields, those are given in the same way by eigenmodes of gravity of Sugra fields in the gravity dual. But now for mesons, we have these eigenmodes of fields on the 8. And I wrote there, how do you find the, I mean, physically, how do you find a mass in a field theory calculation? Well, from the two-point function, you can see that the two-point function in X space decays exponentially, or equivalently, you can find a pole in p squared in the momentum version of that. So let me now consider a little bit of so an analysis about how to distinguish whether the spectrum is discrete or infinite. So so let me consider a space of the type AdS-n, AdS-n plus 1 cross Sm with some non-extremality factor, or sometimes called blackening factor. So u to the alpha, some conformal factor in general, then 1 minus the blackening factor, so 1 minus some constant over um, d tau squared minus dt squared plus dx squared n minus 2 plus du squared over u squared 1 minus dm um plus d omega squared m. And so the idea is a generalization, excuse me, the idea is a generalization of what I told you for AdS with some cutoff in the middle, that will look for the time it takes for a light ray to go from infinity to the center. So let me define in that case the time of flight parameter, which is just dx is d rho square root g rho over gtt. Right, so in other words, I consider dx squared gtt well, dt squared gtt minus d rho squared g rho sorry, down g rho equal to 0, right? And then I call this x time of flight, and I get this result. So I consider this equal to 0. And then it's a simple exercise. Perhaps one could write it themselves. So you just look for the Klein-Gordon equation and consider the motion just in the radial direction. And in the other directions, you write k squared equal to minus m squared. And you define this as minus e. So m squared, you call it e. And then you obtain just a one-dimensional quantum mechanical problem in this time of flight coordinate. So psi tilde is psi modification, a slight modification of psi. So, okay. So you reduce the Klein-Gordon equation, the equation of motion for the field, into a one-dimensional Schrödinger equation with x parameter at the time of flight. Okay. And so then, obviously, the case we started with, for instance, the finite temperature case, so the Witten solution or the black hole, there we had a maximum. We had a finite interval for x, right? We had the maximum x. And then, obviously, this is just really just a particle in a box, right? So then the spectrum is obviously discrete, infinite, and with no accumulation points. So that's clear. But the interesting thing is that it's not the only way to obtain the mass gap. So in fact, the NS5 branes, which we used in both Maldacena Núñez and Maldacena and myself, in this case, so for NS5, we have the string metric was flat. But phi was equal to minus rho. So this was the string metric, E minus phi over 2 times the Einstein metric. So you can go to Einstein metric. But in this case, you will find that V of x is equal to 1, exactly 1. So the potential, and then x ranges from 0 to infinity. So in this case, the mass gap is there to begin with. V of x is gapped, is 1. Although above it, the spectrum is continuous because you have an infinite box. So in this case, you have a continuous spectrum of Abel mass gap. Then for Witten's model for QCD3, which is related to this, one finds in that case, so one finds in that case that there's a maximum x, but v goes to infinity at one side and goes to minus infinity, so something like this. Okay. And so what can you tell about this? Well, this potential, so this starts at 0. So if you are, so you know, excited states occupy more and higher energies. So if you are at this, in this region, it looks like it looks like a discrete set of states proportional to n squared. So this is one of the rare cases of the Schrödinger equation being able to, that can be solved exactly. So there are few cases. I mean, the particle in a box is one, but then this behavior with well, that formula for V of x proportional to 1/4 x minus c squared. Then this gives, so this is mn squared. So this is actually 6n n plus 1, right? R squared. For Polchinski-Strassler, one finds a finite time of flight at infinity and near the core. And then, strictly speaking, then one cannot regulate the divergence. So this Polchinski-Strassler model looks nice, but it has some problems that I did not specify. So you could see them by considering this one-dimensional problem. So for the Klebanov-Strassler, on the other hand, you again find a finite time of flight. So again, you find a spectrum that is discrete. And then in both Maldacena-Núñez and Maldacena and me, you find a potential that, so for M, Maldacena-Núñez and Maldacena and myself, find potential that's 1 plus 1/x or x squared. So at infinity, it's still 1, but in the middle is not. So again, one finds, like for the free 5 brane, you find a continuous continuum of states above a mass gap. Okay, so all of these spectra were of the type considered in here. So for glue ball-like states, where we just looked at eigenmodes for the fields on in the gravity dual. But we can also consider mass spectra from the expansion on probe branes in order to get masses for mesons. So this is what happens in the Sakai-Sugimoto model. So in the Sakai-Sugimoto model, we consider the spectra for the D8 brane. And the D8 brane well, I wrote it somewhere. Oh, yeah. The D8 brane has to be compactified both on S4 and on tau. So we compactify the D8 world volume action on S4, and then you use the solution for U versus tau. That's written again here. And then for the action on the D8 brane, you substitute the ansatz, and you find some action for the fluctuations written on this page 215. So yeah, you expand the gauge fields and the scalars. So there are two types of scalars in this case. They are so where did I put it? Yeah. So there are two types of scalars. There's this, and there's also AZ. So there's an x perpendicular, in this case, U, that is identified with a phi, and AZ. So we have an action in terms of the A mu's, AZ, and phi. And after some calculations, one arrives at the action written in there. So there's a tower of vector meson states, A mu n, and a tower of, and those coupled to some phi n modes. And it's interesting to observe that also this describes the Higgs mechanism. So you see in the action you get A mu n minus d mu phi n squared. So this is what one obtains when considering the Higgs mechanism. Specifically, because that means that by appropriately choosing a gauge, or in other words, redefining, better yet, redefining the gauge field, you can absorb the scalar in it, what people say the gauge field eats the scalar, and becomes massive. Okay, so I'm left with just a few minutes, but that's fine, in which I will describe the bottom-up or phenomenological gauge gravity duality models, which are generically known as AdS-QCD. All right. Let me write here. So these are phenomenological models. And we said that the simplest one was the hard wall model. The simplest, well, that was in some sense top-down, but now let me extend it. Let me extend this hard wall model. So how do we extend it? We add some, the extension corresponds to adding some A mu left and right gauge fields in the bulk that correspond to some SUN NF flavor symmetry in the boundary. So this is the bulk, so in gravity. And on the boundary correspond to some currents, global currents, right? The gauge field in the bulk are coupled to global currents in the field theory. So for some SUNF cross SUNF symmetry. Of course, this is phenomenological because in real QCD we have SU2 cross SU2, SU2 left cross SU2 right, which is an approximate symmetry in the limit where the quark mass goes to 0. And the breaking of a diagonal part of that symmetry corresponds to the Goldstone bosons being equal to the pions. And so we also consider tachyonic scalars, which are bifundamental. So I call them X, let's see, X alpha beta, right? It's m squared r squared equal to -3, which is above the BF bound of -4. So these, again, because we're thinking about SU2 left, SU2 right of QCD, these are Q bar gamma mu TA Q and Q bar gamma mu RA Q. So Q bar left, Q bar right, mu RA Q right. And this corresponds to Q bar alpha Q beta. And we write just the phenomenological part of this model is the addition of these fields with a simple action, just kinetic term. So just usual Yang-Mills kinetic term for the gauge fields. And for the scalars, just a kinetic term with mass equal to -3, mass squared equal to -3. Let me see. Yeah, let me skip this because there's much to be said here. Yeah, let me skip this as well. Yeah, well, I'll skip all of these things because they're not that important. So let me go to the model that is truly new, and this is known as the soft wall model. So the hard wall model was just AdS with a cutoff, and the extension amounted to introducing some fields in the bulk, gauge fields and scalars. But the soft wall model is a modification of that. So yeah, let me write in here also. So S was integral dx squared plus 3x squared, then plus f mu nu left squared plus over 4 plus f mu nu right squared over 4. So this was for the soft wall model. But then the soft wall model, for the soft wall model, the phenomenological thing that we want to obtain is that the mass tower of states goes like n instead of n squared for the hard wall model. So for the hard wall model specifically, I mean, I showed you that the potential was something like this. And in this region corresponding to large masses, this was, one could solve this exactly, and the mass squared goes like n squared. But that's not the correct behavior. We know that the mass squared of excited states instead grows linearly with n, not with a n squared. So the soft wall model came out of the requirement to have this behavior, and also for high spin, we want to have also linearity in spin. And the ansatz is to write, well, a Worf factor e to the 2a of u, dx squared plus du squared. But the non-trivial thing, in the Hardwell model, we would have just AdS, so the warp factor here would be just 1 over u squared. But also, in AdS, we didn't have any dilaton. So the dilaton phi was constant. And now we want to have non-trivial dilaton. And then we have to impose the same kind of ideas we imposed, well, the same kind of behavior that we observed for our various top-down gravity models, namely that e to the 2a times e to the minus 2 phi was log-corrected QCD, log-corrected AdS, or just AdS, which means in this notation phi of z minus a of z. Yeah, I changed from u to z, right? Okay. No, I written correctly. So I written with z is in the middle. So yeah, maybe right just with z. So phi of z minus a of z to be to go like log z, because then e to the minus twice times this is 1 over z squared, which is the correct factor for AdS. And then, so this is uv. And then in the IR, the same thing has to go like z squared. So yeah, there's some arguments for that, which I will not repeat, but roughly speaking is that then the exponential of this when z yeah, so the exponential of this is very large. So then a solution, the simplest solution to these two constraints. So remember, we're doing phenomenology, so this is really a solution. So phi minus a is just the sum, so z squared plus log z. Right? This solves both constraints. And the action is basically the same one, just that now we're considering the dilaton, and in the string theory, in string frame, what will happen is just I have an e to the minus 2 phi in front of the fields. Sorry, e minus phi, not 2 phi. No, right, it's e minus phi. No, why is... I thought it was e minus 2 phi. Okay. Okay, it might be a typo. I think it's e minus 2 phi. Anyway, then Right. So then we can consider the action for the various fluctuations. So I've written for you before the action um, the solution for the case of a single scalar field in the presence of a dilaton. Now it gets a little bit more complicated. And so then this behavior was such that I get mn squared proportional to n. So one can even construct an exact potential that will correspond to our simplest choice of phi minus a being z squared plus log z, and that's written on page 220, this Vn of z. Yeah, decay constants I haven't told you about. But so now this fixed, so through this behavior we fixed phi minus a to be z squared plus log of z. But that does not fit individually phi and a. To do that, one must consider the second condition. So the first condition, that mn squared was proportional to n, allowed us to fix phi minus a. And the second condition, that if I introduce spin, this is also proportional to the spin, leads to a condition independently on phi and a. There's some details there that doesn't matter too much, but one obtains that one restricts, in this case, phi minus s. One restricts 2s minus 1, sorry, 2s minus 1a. So effectively then, with this condition, one condition on phi minus a and one on phi minus 2s minus 1a, one fixes independently both the dilaton and the warp factor a. And the final words I have to say is about something called improved holographic QCD, which sounds impressive, but it's not quite as impressive as it sounds at first sight. So improved holographic QCD is a method by which we propose to obtain the wanted running coupling constant. So running coupling constant is certainly a behavior of QCD that needs to be taken into account. So it was obtained in some of these top-down models, right? The problem is we don't know the running coupling constant in QCD. We just know perturbatively a few terms. So the ansatz for the running coupling constant that we consider is obtained from integrating out just the two-loop beta function. So just two-loop in QCD gives us a proposed behavior for how this lambda changes with mu. And then considering, let's say, a v of lambda, which is g squared n, or GSN, and then this is e to the phi. So potential for GSN, but where GS is e to the dilaton, one considers such a potential that gives rise to this beta function in the dual field theory. However, this is not so when considering that, we write the Einstein equations and we obtain some complicated metric. But it's important to realize that what does it mean to match this? So this was from beta 2 loop of alpha S. Well, beta 2 loop is the beta function of QCD in the UV. And this is behavior in the IR. So it's kind of assuming somehow that this 2 loop beta function is still valid in the IR, which is certainly not true. So it's improved in the sense that we add some running coupling constant, but it's phenomenological in the sense it's an extra phenomenology in the sense that we assume this 2 loop beta function to be true in the IR, which is certainly not the case. So that is actually everything I wanted to tell you. So this is the end of my set of lectures. So now questions, please.
So at the beginning you said that this kind of ADS QCD, either bottom-up or top-down modeling has been losing some traction over the last years, I believe. So I just wanted to know well, first of all, what does the AdS-CFT field look like in general today? And why do you think that that the modeling of QCD is has been losing traction? Some of these models seem reasonably promising.
Well, I mean, this is just because, you know, to some degree is a sociological issue, but it's reasonable because we always look for something where we can make some more contributions. And after writing all of these models, there's not much else you could write down. So you have, I've told you the principal top-down models, the principal bottom-up models, and everything else is small variations and trying to calculate some more things. And, you know, all of them are not really QCD. So in all of them, you just calculate stuff, and then you say, ah, look, it looks kind of like QCD. And so the more important problem with all of this, both top-down and bottom-up, is the lack of control over corrections. So, you know, it's one thing if I could tell you the result of this model, let's say Sakai-Sugimoto, is this for the mass spectrum plus or minus this. I don't know about plus or minus. I cannot tell you. And, you know, that's the end of it, right? Because you just say, well, it's close by. But the plus or minus, that's where the hard part is. You know, it would involve you being able to say something about the corrections beyond the models you're looking at. And you know what approximation you made, but the value of the corrections, you cannot say much more. The only thing you know for sure is that large n means you have 1 over n squared corrections. And so, but that's, you know, that people knew from lattice QCD. They would always say that, you know, probably since NC equal to 3 in the real world, it's 1 over 9, which is about 10% corrections just from large n, right? But then there's all sorts of other assumptions, you know, probe approximation. This is one, okay. You might say some things go like NF over NC. Okay, but NF over NC in what compared to what, you know? And yeah, so all of these things don't have a good, I haven't seen anybody having a convincing argument about what the corrections to a particular calculation are. Okay, so that's basically the problem as I view it. And then there's just tiredness, you know, people say, there's 100 papers on looking for the masses of I don't know what particle. I don't want to write 100 first. Let these other guys do it, and these other guys get pushed to, you know. So that's the sociological part, because people are looking for the next interesting, cool thing. But yeah, there's this fundamental issue because of the corrections. You don't really know. There's no progress, to my mind, been made in fixing the corrections. Yeah.
Well, first of all, thank you for the mini course.
Thanks.
It was pretty nice. You didn't comment that much during this week about applications to cosmology, and I know there's something called celestial holography, which sounds something interesting, and I was wondering if you could comment a little bit on that, your views on that.
Well, so celestial holography has not reached the point where you can actually apply to cosmology. There are various reasons for that, people just speculating, but I thought you were going to say something that I've been working on for the last few years called holographic cosmology. Problem with that is that not everybody agrees on what that holographic cosmology is. And because of that, I didn't want to get into it. I had written a few slides which I actually ignored on holographic cosmology, simply because I wanted to tell you only the things that are, you know, 99% sure, people that almost everybody agrees with. If I told you about holographic cosmology, I would have to tell all the caveats and all the people who disagree. And but yeah, that's to my mind, to my personal view, is where new interesting things are happening. But many other people disagree.
So it's not about this particular lecture. It's more about the general context. I think he touched it a little bit in his question, but so AdS-CFT is usually introduced as a conjecture. You didn't really mention it, but from what you showed, it looks like the generalizations are mostly applied in this, let's say, phenomenological approaches that you mentioned. So is that where the conjecture come from? Or is there more, let's say, general setting where you can say, like, it's a conjecture because this particular reason?
Well, so it's, people say it's a conjecture, but at this point, it's kind of pedantic. Yeah, so the point is in the original AdS-CFT, I've showed you the heuristic derivation, And there are even other arguments. I gave one such argument a few years back, and other people are looking for a bit more rigorous arguments. But my particular argument and these other as well were referring to specific dualities. So the original one with AdS-5 cross S5. And so, but as a physicist, you might say, well, in these original ones, it's just pedantic because they have hundreds of tests. So you don't, a mathematician might care, but, well, you might care in the sense that by proving it, you learn something new. That's another thing. But from strictly speaking, calling it a conjecture, you learn nothing. But in the other cases, in the cases of gravity duals that are not, let's say, the phenomenological ones, for instance, it's not pedantic at all. It's not completely, not at all clear that this is true. It's conjectural based on a lot of things we have learned, but there's not even a heuristic argument. So it's more of, you know, our familiarity with calculations that led us to believe this is true. So yeah, I mean, in those cases, we would learn a lot if we could have any kind of proof, even a heuristic one. Yeah, so in the top-down ones, we know both sides, and but in the phenomenological ones, we don't, and then, yeah, this would be very useful. Yeah. Listen, let's take a 10-minute break because until 3, because I need to do a few things, and then we'll start with the last question section.